So let's start our work. Today we have Lucia Klein with the talk about changes in flare-associated flares, magnetic field in chromosphere and photosphere. Lucia got her PhD in 2010 from Zurich ATH. She was a postdoc at HGO in 2011-2012. And research scientist in Lockheed. Now she shares two positions, one in Switzerland on Marie Curie Fellowship and now teaching math, and also she is scientist at Leibniz Institute for Solar Physics, and Lucy is currently head of the German Solar Telescopes, including Gregor and VTT on Tenerife. So please go ahead. See, you have your 45 minutes. I'll give you warning 5 minutes before.
Okay. Thank you very much. Can you hear me? Is this okay?
Yep.
Okay. So welcome everybody. Good afternoon. I would like to talk about today about photospheric and chromospheric magnetic field changes during solar flares. And I invite you, I'm open to questions even during the talk. If I don't explain something well, or if you have questions, please just interrupt me. We start about flares. We should first look at how flares work. What we know is called the Standard Model, and in a very simple picture, it's drawn here. So we know that flares start by reconnection of the upper atmospheric magnetic field, which here in green, and this reconnection accelerates particles towards space and the solar surface. Particles are decelerated as they enter the more dense and denser atmosphere. They emit X-rays, Strahlung. That's why we see foot points of usually 2 foot points at the end of the loop. They also cause heating, which is visible as ribbons. Here in yellow. The problem is, while we know the general picture, we don't really know why flares start. We cannot predict them, we do not understand the energetics completely, and small-scale processes we do not know yet in that much detail. What I would like to focus on today is how the magnetic field is changing at the foot points of these flares, in the lower solar atmosphere. So the main question today is, how is the magnetic field structure changing during flares? And that's important because some of the energy is lost that way. To actually understand the energy in flares, is important to also calculate how much energy was there in the beginning, what is the free energy that can power flares. So in this talk, I will compare photospheric and chromospheric magnetic field changes, not the coronal ones. Then I will also, in the second part, compare it to modeling, because if models can reproduce these changes, it tells us that the models actually follow what is happening on the sun. And from that, one can derive the free energy then. Known that flares are very global phenomena. This movie shows an animation of running differences, meaning each preceding image is subtracted from the next. And even though the flare happens in a relatively small area of the sun, just in a sunspot, its effects are everywhere, basically. You see the shock wave propagating, you can see how the magnetic field lines change, some temporarily, some permanently. And one can see that the propagation is not similar everywhere. For example, it goes, in this case, more north than south on the sun. These changes are different in each flare. And the interesting thing is, what is exactly happening locally? How is the magnetic field really changing where the flare is happening? Simple picture, we have particles coming down along the loops. And these particles need to lose their energy somehow, because within a few minutes, it releases 10 to the 32 ergs, more or less. And This energy has to be dissipated, and we know most of it is dissipated by radiation. Radiation meaning continuum enhancements, spectral lines. And some of the energy is used to power other stuff. Like, for example, there is heating, obviously. There is mass motions. That means kinetic energy. There are sunquakes. There are also changes of the magnetic field. Just to give you a context on this energy, it's the largest ever atomic bomb is a few 100 billion times less than a regular flare. Dissipate this energy very fast, and we have to understand how it's dissipated to actually understand all the flare processes. So far as we know that the photosphere is changing. We have seen that many times. In the 90s especially, it was discovered by Wang, Kosovichev, Tarkova, and so on. And what these authors reported is that the magnetic field changed abruptly, not continuously, but abruptly during flares. And later statistic studies have even shown that it's on average a quite large change, something like 90 Gauss in one study. Changes, photospheric changes, are quite well known. They have been studied. And in one example I'm showing here in the movie on the right is a photospheric change, which also changed the structure of the sun. It shows a movie of HMI. In that red circle, you can see a penumbra, then a bright flash, and then half of the penumbra is gone. The lower part is gone. That is white light emission, meaning continuum emission. And the penumbra that is gone, this is a change of the magnetic field, which at that point is no longer horizontal, but either gone or vertical. Are relatively well-known photospheric observations. Now the problem is the chromosphere. Chromosphere, we have no spacecraft to do this regularly. We have ground-based observations, which, however, are limited by field of view, day-night, seeing, and cadence. Up until now, there, to my knowledge, is only one observation which has sufficient cadence and coverage and caught a large flare to do this analysis in the chromosphere. And this is the observation I'd like to show today. The magnetic field in flares is, as I said, not very simple. There have been several, but not too many observations of chromospheric magnetic fields. One is shown here. That was by Dato Kuric et al. Just last year. And they managed to catch a large flare just at the solar limb. That they could derive the line of sight magnetic field. And if you look at the lower plot, the signal is not very strong everywhere. Where there is white, it means it was not possible to determine the magnetic field. And that's generally an issue with chromospheric observations. We do not have enough sensitivity, and therefore we cannot determine the field everywhere and at the cadence we would like it. If I look at our observation, you can see here a zoom with HMI. This is the HMI resolution. This was the sunspot that flared. This is now ground-based observations. And by changing wavelength, we can step in height. In this case, we have now reached the chromosphere, and you can see what a challenge it is to actually catch a flare, because the field of view compared to the big solar images of HMI is tiny. In this case, we have 40 times 80 arc seconds. It was the EBIS instrument. More or less by accident, we were pointing exactly perfectly centered where the flare is going to happen. The task is, we want to know what the photosphere is doing. Photosphere, we have HMI data. We also have EBIS data in the 6302 spectral line. We'll present here the HMI data because the EBIS data are basically very similar. Are more noisy due to seeing, and therefore HMI was considered more stable and better to show stable magnetic field changes. The goal is to analyze the evolution of the magnetic field change in the line of sight. If we look at the evolution of the magnetic field, we can fit a function to determine if it's changing normally or very fast. In this case, this function was proposed by Sudol and Harvey in 2010. And the special thing about this function is, or the nice thing is, it has an arctangent function which clearly describes the step of the change. Terms A plus B, they just show the linear evolution and the offset of the magnetic field. So it's possible that the magnetic field would be increasing simply as a linear function, in which case the right part would more or less be zero, and just A and B would have values. If the right part is not zero and shows a jump, then we can automatically determine how the magnetic field is changing, with what size, and with how fast, in which time range. The plot shows an example. This was half an hour of observations of HMI. This is 1 pixel of HMI. And the line of sight magnetic field changed very fast from something like 700 Gauss, 400 Gauss. It's a 300 Gauss jump within a few minutes. That's exactly what we are looking for, these fast changes exactly around the flare. The same analysis was done for the time before the flare and after the flare, and there were not so many strong jumps. There are very, very few, they're always there, but these strong jumps of a few hundred Gauss, they're limited to flares. Again, the evolution of the magnetic field of the day of the flare. That was an X1 flare on March 29, 2014. You can see that the magnetic field is obviously evolving. In most cases, it's evolving linearly, not jumping right at the flare. And all this linear evolution, that would not be analyzed because it would not give this strong jump that was one of the criteria to select a pixel for analysis. So 2 examples. One example, as I shown before, in the pore above the sunspots, there is magnetic field changing by more than 300 Gauss within 3 minutes, more or less. If we look at the umbra of one of the sunspots in the bottom plot, we can see that the fit is not good, that there are some data points around 17 o'clock, 17:45, which are not fitted well. And these data points are probably because the spectral line was in emission, or at least its shape changed. And that will influence the mechanism how HMI derives the magnetic field. We can say that these data points are probably spurious and not showing the correct magnetic field value, which is why we had to repeat the process fitting at points. So the fit I'm showing you here is not the final fit. This is just to show you an intermediate step. This was later then corrected, points were excluded, and the fit showed a smaller jump, something about 200 Gauss. This shows you how much there is to consider. And in the end, it was deemed most reliable that I simply looked at every single fit by eye, decided to discard the ones which looked bad. Fit for a pixel, we could create a map of the magnetic field changes in every single pixel. The image shows in contours where the sunspots are. There is the big sunspot on the bottom and the smaller sunspot more towards the middle of the image. And everything which is colored here means the magnetic field changed there. There were many changes in the middle of the image, which was, by the way, where the neutral line was between the sunspots. There are some changes drawn in red where the small pore is. There are single pixels which also may have changed, but in largely the areas are coherent. What's also drawn here is how where the small sunquake was. This is these red contours, and one can see that it did not coincide with these magnetic field changes. So from that, we have a map now of the photospheric magnetic field changes. And now we do the same for the chromosphere. Just with the chromosphere, as I said, it's not so easy to get magnetic field values. Problem here is not only the ground-based and varying seeing, but it's also that the method to get the magnetic field is here the weak field approximation, which works quite well for this spectral line, but may not work for all spectral lines. So here we have the observations of the chromosphere. This movie shows 1.5 hours of that flare. You can see that the seeing is slightly varying as it gets blurry and in focus again. But what you can nicely see is that filament here, which later erupts. And then the flare starts with 2 ribbons. And field lines seem to, or at least loops, become visible between the 2 ribbons with bright loop tops. So please remember that filament, which was there in the beginning, because that will be important later for the modeling. The modeling structure will show something similar. And what's also interesting here in this movie is that there was, I don't know if you can see my mouse, but here there was some flux rope just below the small spot. Flux rope vanishes at the end of the movie. So it's very clear that the chromosphere is changing much faster. It has much bigger changes, and that these loops are somehow affected by the ribbons that sweep through them. We derive the magnetic field from that. Same movie in all polarization states, QUV. Q and U, to get the horizontal magnetic field, are not so good to analyze because they usually have very, very small magnetic field or very small polarization and therefore not unreliable magnetic field values. Stokes V was selected because it had strong polarization, especially where the flare was. What we can see here is we pick any pixel. In this case, we picked the pixel here in the black area of the magnetogram. And that pixel had a very deep absorption line, but some emission in the blue wing and some absorption in the line center. From that, we calculate the derivative of Stokes I and compare that with Stokes V, which is shown in the bottom plot. By scaling the derivative of Stokes I with a factor, we can determine the magnetic field. The formula is given on the left. So it's basically this delta lambda H is directly proportional to the magnetic field value. That's all there is to the weak field approximation. We did the scaling in 2 ways. One is taking into account the full spectral line, and one is just taking the blue wing. The comparison, because if the line is highly asymmetric, this method is probably unreliable. Only kept pixels where both the blue wing and the full spectral line showed a more or less similar result. Also discarded all pixels that were noisy or did not give good fits. So anything with polarization below 2% was automatically omitted, and that's why there are also these gray areas in a magnetogram. We could do it for every single pixel, and we got a magnetic field value in every pixel, every single time step in 1.5 hours. And then again, with the arctangent fitting, we could derive the chromospheric magnetic field changes. This is an example of one of the pixels. This is completely in the middle of one of the flare ribbons, shown on the right with the red cross. In the chromospheric magnetogram, it's more or less at the polarity inversion line. And when we look at the evolution of the magnetic field, that it's changed also very fast, within 3 minutes, in this case by 500 Gauss. There are many pixels like that. Now can also see that the scatter is much larger than in a photosphere. This is because of seeing. There are time steps when the seeing was blurrier than at other steps, and that gave a different magnetic field value. Overall, it's quite coherent, I would say. That for every single pixel, and we get the following map for the chromosphere. Every single colored pixel here means the magnetic field changed stepwise, and the magnitude of the change is with the color bar. One can immediately see the changes are much larger, both in area and strength, than in the photosphere. We seem to avoid the location of the sunquake. What we conclude from this is, first of all, the method seems to work because the pixels are very coherent that show changes. It should not be small misalignment of the observations. It should not be an instrumental effect. It seems that the changes really happen in bigger areas. See that there is more or less a factor of 2 in magnitude between photosphere and chromosphere. Compare. The photosphere is on the left, the chromosphere is on the right, and everything, all these colored pixels are overplotted, meaning there is a stepwise magnetic field change either in a photosphere or in a chromosphere on the right. And if we now compare, we see that the photospheric changes, they agree with one part of the chromospheric changes, where the red arrow is pointing. But there is a huge area in the chromosphere, where the yellow arrow is pointing, which only seems to be changing in the chromosphere and not in a photosphere. At least to me, unexpected. I expected these layers to act coherently, to be similar, but it seems that photosphere does not see anything of these chromospheric changes. The magnetic field seems to be quite constant there and not varying at all. So now we can start to investigate why this is happening. We overplot the changes also on the AIA images, which show the coronal features during that flare. And if we look at the photospheric changes, well, they are not correlated definitely with anything in a corona. Are different, foot points are in a different spot, the center of the flare is in a different spot than the changes. It seems that the photosphere does not know anything about the loops above them, at least in this case. Chromosphere, what we can see is that most of the changes to coincide with endpoints of the loops, especially this large area, which I show with the red arrow. It seems to be that this is the end of these smaller low-lying loops, and also the foot point on the right of this big loop where chromospheric changes were seen. So it seems that the chromosphere is more governed by the upper structure, or the chromospheric changes. Now the next question is, do these magnetic field changes coincide maybe with X-rays? Because we know that X-rays coincide with white light emission. There is a paper by Sam from 2011, which shows very nicely that the hard X-ray contours match nearly perfectly with white light ribbons. And also a paper by Petter Heinzel that also off-limb, the match is near perfect. Expect that if the mechanism is similar for magnetic field changes and white light, there might be also similar locations that would imply that we could understand them better. If we overplot the hard X-rays, the changes, we can see, well, there is not really much overlap. It's actually the magnetic field changes seem to rather avoid where hard X-rays are. The main contours going to the big sunspot, those are very prominently located where no magnetic field changes occurred. Other sunspot, it coincides, but that was the weaker source in X-rays. What we can conclude from that is that white light and hard X-rays do not seem to be closely correlated to magnetic field changes, at least in this flare. If we now look at the geometry, we can maybe conclude what is actually changing on the sun. We know that on the left part of the field of view, the magnetic field is becoming larger after the flare. And in the right part of the field of view, the magnetic field is becoming smaller. We know the position of the flare on the sun. The white arrow is showing where disk center would be, so it was not exactly at disk center, but more on the top right of the sun. And we can reconstruct that if the magnetic field is changing that way, how could the loop be changing? A model by Hugh Hudson, which predicts implosion of magnetic fields during implosion of loops, not magnetic fields, during flares, which means the loops should contract and therefore go in a lower energetic state. If the loops would contract, that would give the opposite change of the magnetic field that was observed. At least in this case, we can say, no, the loops have not contracted here. It could be increasing, but that has also not been observed. One explanation that we propose is maybe the loops were twisted before the flare and they became untwisted and more straight after the flare. Shown in the bottom right in this plot. Top view looked like a sigmoid before the flare and then became more straight in the bottom row after the flare. That might explain the observed magnetic field changes. This is simply a phenomenological explanation. We don't have 3D magnetic field information yet. It would actually be very interesting to measure new telescopes. The second part that I would like to talk about is modeling. We have done nonlinear force-free field modeling that was in collaboration with the group of Mike Wheatland at the University of Sydney. And they calculated all these models to compare if the models can reproduce the observed magnetic field changes. Nonlinear force-free field modeling requires an assumption of a base magnetic field distribution, and for that HMI was used. And every 135 seconds, there is a vector magnetogram from HMI, which was used as a boundary condition. The extrapolations gave two solutions, one based on the negative polarities, one based on the positive polarities. And if we look at the solutions, we can immediately see that the positive polarity solution is much better or much more realistic. We can see this red filament in the P solution that matches quite well with the filament that we actually observed in the chromosphere in the movie. From now on, we will only keep the P solution and discard the N solution, and we will fit the same arctangent magnetic field change model to derive if the magnetic field changed also in the same way in these nonlinear force-free field models. First, we have to determine the actual height we're looking at. So the model obviously only has a base, that's the photosphere, and everything above the base is extrapolated. So we take the height index 0, the lowest one, as photosphere, and every step in the model in height was calculated with a distance of 725 kilometers. Now the calcium 8542 line that forms probably below 1,500 kilometers, potentially slightly above 725. But by comparing the magnetograms, we could see that the height index 1, the 725 kilometers, seemed to match most closely to what was observed. So that's why we took this index as the chromosphere. The comparison of the different magnetograms shows this color scale to show you how magnetic fields, meaning above 1,500 Gauss, are different in these different heights and data sets. On the top left, we have the HMI 45-second data, the normal B-loss line of sight data, and one can see that the center of the umbra is not very black in comparison with the image in the middle, which is the 135-second data set. It is well known that HMI 45-second data underestimate the strength of the magnetic field. And therefore, maybe the jumps that we saw are slightly below what they really would be. This is the strength of the jumps. On the right, we can see the non-reinforced free field model, and there the match is quite good. Well, obviously, since it was a boundary condition. In the chromosphere, we have a smaller field of view given by IBIS, which is the bottom row. And there we can see the magnetogram from the extrapolation, which also matches relatively well, at least in structure. Everything which is gray in the observations of IBIS, that was simply because there was not enough signal to determine the weak magnetic field. Results. We have the observations in the top row, the modeling in the bottom row, the photosphere on the left, chromosphere on the right. So if we look at the photosphere, the observations show the changes mostly at the neutral line, as I showed before. Modeling also shows the changes there, expected because it was a boundary condition, but also there are some changes reproduced by the model. Especially in the bottom left, there is a big blue patch which was not observed. It seems that these models also do something in a photosphere which is not completely realistic. If we look at the chromosphere, the right column, then we see that the chromospheric changes, the observed ones, happened mostly at the loop foot points.
Alicia, can you clarify the background image? Is this field or difference?
Magnetic field change.
Change. Mm-hmm.
Yes, always change. Yeah, you're right. The label should be adapted. Yes, so here the red area, that means the magnetic field changed by 300 Gauss within about 5 minutes. On the bottom plot in the modeling one, we see a big blue area, which does not coincide with anything else. So that means that the model actually reproduced bad changes or reproduced changes in an area where they were not observed, mostly at the loop tops and not at the loop foot points. The question is why? So one explanation is that we are simply not looking at the correct height, but I did this analysis at many heights and proof. Another explanation is maybe force free is not a good assumption. Maybe it's because simply the changes happen on such small scales that this model cannot get them. The physics of the chromosphere, all these tiny loops which were seen to be changing in the movie, they simply might be missing in a model. Right now, this is unsolved. All we know is that the fit is not very good in a chromosphere. That's the overview of the March 29 flare. As a last part, I would like to show you more statistics. Statistics, we have HMI, which observed many flares, and one can do this analysis for many, many other flares. And Sebastián Castellanos Duran, who was a master's student working with me at Fachhochschule and now is a PhD student at Max Planck, he has done this analysis for 75 flares. Unfortunately, as I said, there are not enough chromospheric data yet to do this. Hopefully, with new telescopes, we will also have statistics there. Here is an overview of 75 flares that were analyzed. Ranges from X, I don't know what the biggest one actually was, X, many X's to C-class flares. And they were selected to be everywhere on the sun, all kinds of sizes, distributions, to have a representative sample. And what we found is that the magnetic field changes showed up in every single flare bigger than M1.6. This might simply be an observational result because the areas got smaller and smaller with smaller flares. So it might simply be that we don't see them in the small flares, but that every single flare might be changing. And most of the changes happened near the polarity inversion line. These two single results I would like to show in more detail. In this plot, on the x-axis, you have the flare strength, so Gauss class, basically. There are C-class, M-class, and X-class flares. The colors of the different data points are limb distance, which was also scattered basically everywhere. And the y-axis shows the area where the magnetic field changed stepwise, not slowly. And as one can see, it is a power law because it's a log-log plot, and bigger flares have areas of changes of the magnetic field. One can also see that as one goes to C flares, the areas get relatively small, 10 megameters, which simply might not be resolvable in HMI. All these areas were corrected for foreshortening, and there is absolutely no dependence on limb distance. The result is that most of the changes happen exactly or very near the polarity inversion line. Here the x-axis is the distance from the polarity inversion line. The y-axis is the strength of the magnetic field change. Changes happen right at 0 or 1 in x. And then there is an exponential decay with varying distance. In numbers, if we look at all the changes bigger than 250 Gauss, 90% of them happen within 9 arc seconds of the polarity inversion line. And so far, this is also an observational result. There is no very clear explanation yet why there, and especially why in a chromosphere it's in a different place. Studying right now is magnetic field changes are related to white light emission. All these flares also showed white light emission, and in these plots, the thing which is shown in red is that white light and magnetic field changes overlay. Blue means just magnetic field change, and green means just white light. And one can see that there is some overlap, but it's not really perfect. That was also seen by this X1 flare that I showed before. In most of the cases, 64% of the cases, the magnetic field change area is larger than the white light area. But again, that could be an observational result because we may simply not be seeing the small changes, white light or the small changes in the magnetic field. And this paper deals with how big the areas are, what the dependence is, and how many flares show both white light and magnetic field changes. What to do is atmospheric magnetic field changes. I would like to have D-KIST observations which show these magnetic field changes, which show flares, and I will definitely try it with Gregor, as we are planning next year to have a Fabry-Perot imager installed there, with a relatively large field of view, something like 50 arc seconds squared, and then we will also be able to catch flares with Gregor in spectropolarimetry in chromospheric lines. To summarize, this famous March 29th flare, and I made a typo with the year, we have the photosphere and the chromosphere. In HMI, we see changes below 320 Gauss, and we have the chromosphere, which shows much bigger changes, factor of 2, in bigger areas. And what is puzzling for me is that they seem not to be really related. The areas are different, the locations are different, and in some cases, even the timing is different. Chromosphere is not yet reproduced by models, the chromospheric changes, I mean, and it would to have more statistics instead of just this one flare. What the changes tell us is that this is not really compatible to shrinking loops. It might be compatible to increasing loops, which, however, have not been seen, or loops that untwist. Hopefully, future observations will have full Stokes polarimetry, not just Stokes V, which will allow us to determine the three-dimensional magnetic field. Thank you very much. These questions.
Yes, thank you, Lucia. Now we open for questions, so please go ahead, unmute your microphone if you have question and ask. So far, all microphones are muted. So let me ask my question, and maybe later on, other question will I will be asked. So my question is, in fact, about this comparison with extrapolations. So Mike is using mathematically sound Grad-Rubin approach to reproduce, reproduces 3D structure with has both advantages and disadvantages. So the advantage is that this mathematically well constrained problem. Disadvantage is that photospheric condition is not consistent. And this is, in particular, this is why you have different P and N solutions for the same boundary condition. So your boundary is consistent with a number of different nonlinear force-free solutions, in fact. So my question is, in fact, if I provide you with models with a data cube obtained with different methods, are you interested to look in those? You can just
Yes, please.
so I can do it by the end of the day, because so if you provide me with your PowerPoint presentation where all needed information about times and field of view is available, I'll provide you by the end of the day with 2 data cube, and you can then investigate.
You need one data cube every 135 seconds. So for every HMI observation.
But what you showed us a single difference, I believe.
It was tangent fit. It was a fit to half an hour of data.
You mean this in those?
Yeah, he did this extrapolation every 135 seconds.
Yeah, I was thinking that if you have a model before and after, you may just have a direct look there, not.
Problem is because this active region had a lot of flux emergence. The evolutions are sort of linear. So if I take just 2 values, yes, they will have changed, but it was a linear change. I'm more interested in these jumps of changes.
Okay, so it's a little
That's
bit
why
more.
we did the full half an hour of observations.
Okay, so we can maybe talk offline about that.
Yes, definitely. If you have another extrapolation method, I would be happy to fit the function and check if it's changing there.
Okay, Hugh, do you have a question? Please go ahead.
Just a further comment about the N and P. Not legitimate to pick one is better, because I think from Maxwell's equations, from the point of view of Maxwell's equations and a static situation, the extrapolation should be identical for both choices. So if there's a difference between the two choices, it is kind of an error bar simulation. It isn't a, and so I don't think the simulations are particularly trustworthy in the non-force free region, and so I think that's a good measure of how uncertain they are.
Yeah, I'm not an expert on this. I have seen differences in PNN in the past.
That's a flaw in the MHD approach in general, I think, because the PNN should match exactly.
Theoretically, probably yes.
Yes, Hugh, they have to match in real life, because real life deviates from force-free state. Yeah, force-free. But if you like force the force-freeness, then you have this inconsistency between method, Grad-Rubin in this case, and the boundary condition. For the force-free solution with Grad-Rubin, the boundary condition is over determined. So you have more constraints than you need to constrain.
Inconsistent constraints.
Yeah. Okay. Other questions or comments or opinions? Sorry?
My opinion is that's not, it's nice.
Okay, sure. So if we don't have questions right away, so let me thank our speaker once again. Thanks, Lucia. It was really very interesting and in particular very nice statistical development of something some of us knew already. So thank you very much. Join us in 4 weeks for next.
Thank you for the organization.